Welcome back, grade 12s, and we've got our last example here where we're given a diagram with loads of information. And in fact, see if you can spot it before I do it at the end of the video. We can solve for theta in the diagram because we're given so much information. Because there's a circle, and a circle just gives you so much. Anyway, let me stop getting excited by that, and let's get into the trig part of it. So we're given AB is a diameter, and we've got A, an isosceles triangle. We're given a tangent. So there are loads of things. We might be thinking of angle in semicircle, tan chord. There are no angles in same seg. But all of those things. There's no cyclic quad yet. We could construct things. So let's just write down things we know. Well, if that's theta, if DC is a tangent, then just with tan chord, I think it makes sense. Well, let's just label that theta already. But that one we're definitely going to need to give a reason for. So C1 and 2. B1 and 2, so C2 equals theta because of tan chord. Okay, useful reason that we use so often. And we've got an isosceles triangle, so that one there, D must also be theta because of that isosceles triangle. Well, then B1 we can just get from angles in triangle. Well, that's 180 minus those two thetas over there from some angles triangle. Okay, well, probably got enough information because we're trying to work out DC. Well, there's DC down here. And we've got the angle opposite and we've got those two sides. And it's already got a cos, so it feels like cos rule, but just be careful because, in the previous example, I think we saw sine change to cos because we had a 90 minus. So that's not always a good indication of which rule we're going to use. But we've got DC, we've got angle up, we've got kind of a side angle side idea going here. So since we've got that SAS going, let's use our cos rule. DC squared equals A squared plus A squared minus 2A. Oh, my writing's needing a little bit of work here. AA cos that angle in between, which we said was 180 minus 2 theta. Okay, just our standard cos rule. And that's got all the bits of the puzzle we need. It's got thetas and A's and DC. So we're going to have to square root a bit later by the looks of it. So I'm going to leave that as DC squared and just simplify the right. A squared plus A squared, 2A squared, minus 2AA is 2A squared. And cos 180 minus 2 theta, well, wait a second. That's just negative cos 2 theta. So that's negative cos 2 theta. I think that clearly shows that was the only one we had to change. I think that clearly shows the negative cos 2 theta. Okay, well, what's nice now is we need to decide which of our double angle formula we're going to use for cos 2 theta. And to my mind, it's not quite clear at this stage. So I'm going to factor out a 2a squared. Maybe it will help us see which one to use. Because I don't know, out of the ones, I'm going to use the cos squared one, the sine squared, and cos squared one. I'm not sure. So if we factor this out, we're left with that. Now this really makes it feel a bit more obvious because so often when we see that 1 plus, well, we're going to use the minus 1 so that they can kind of cancel each other out, right? So we can use the 2 cos squared theta minus 1 identity so that you got the 1 minus the 1 and we just left with 2 cos squared theta. So therefore DC squared equals 2a squared times 2 cos squared theta. Well, 2 times 2 I hope is 4. A squared is a squared and cos squared theta is just so. So if we square root the left hand side and square root the right hand side and think in terms of positives, then we've got DC equals 2a cos theta, which is what we're required to prove. Now at the beginning I got all excited because I said, now wait a second. We could actually solve things over here and say, this angle here, B1, we said now was 180 minus 2 theta from the triangle BDC. But at the beginning I also said we could use all sorts of things like the fact that AB is a diameter, and so we could use angle in a semicircle. So C1 is 90 degrees, right, from angle in semicircle. Zoom. Okay, which means that B1 from exterior angle of triangle, well, that's just 90 plus theta, right? From exterior angle of triangle. This is going to go behind my head, and that's fine because you know what I'm writing. Exterior angle of triangle, it's there somewhere. Well, now we've got two ways of writing the same thing, so they're equal to each other. Or in that triangle, if we add all those angles up together, we've got 2 thetas there from D and C. And this part here is 90 plus theta. And angles in a triangle, last time I checked, added up to 180. So behind me, what I'm writing is some angles in triangle. Angles, triangle. Well, one day I'll get back to moving around the bottom. I disable that function. Okay, so we got a little equation to solve, and 3 theta plus 90 equals 180. 3 theta equals 90. So theta must actually be 30 degrees in this diagram, which means we could solve this and work out cos theta, root 3 over 2, and simplify this. So the diagram's actually a bit more fixed than it first seems. We indeed have 2 variables only. Wait, we've got just the one, A. And DC relies on what A is. So just A is going to determine what this diagram looks like. This angle is fixed. This is fixed. All these angles are actually fixed. Interesting little aside. See you in the next one if there's one.